Shonak, who will introduce the speaker. Thank you.
Hello, everyone. I have the great pleasure of introducing Professor Alejandro Frery. He received his BSc degree in Electronic and Electrical Engineering from the Universidad J. Mendoza in Argentina in 1985. His MSc degree was in Applied Mathematics, including Statistics, from the Instituto de Matemática Pura e Aplicada in Rio de Janeiro in 1990. And his PhD degree was in Applied Computing from the Instituto Nacional de Pesquisas Espaciais, which is the National Institute for Space Research in São José dos Campos, Brazil in 1993. He's currently with the Victoria University of Wellington, New Zealand. He's an IEEE distinguished lecturer and spends a lot of his time educating audiences around the world, much like us. Apart from this impressive biography, I have the privilege of being able to introduce him at a more personal level to our audiences. So here are some facts about Professor Frery in no particular order. He's an avid fountain pen enthusiast who loves mixing his custom ink colors. His work philosophy is centered around doing something interesting first and then worrying about publication of it. Under his leadership, the average response time for GRSL, which is Geoscience and Remote Sensing letters, substantially reduced. So you have him to thank for quick publication of your letters. And he's a very big proponent of reproducible research and believes in sharing code and data as far as possible. With that, everyone, I hope you applaud virtually for my favorite and soon to be your favorite, Professor Frery.
Thank you very much, Shonak. Thank you very much for the organizers of this meeting, the San Francisco chapter and the Colorado and Highlands, or I don't remember exactly what chapter, joint chapter initiative. And I think we have some participants also from Brazil, Argentina, and Peru for what I have seen. Well, I'm very glad to be here with you with this talk. We will talk about the use of statistical information theory and briefly about statistical information geometry in image analysis, in particular in SAR image analysis. But let me start by saying that everything that I will present here can be applied to any situation in which we have a statistical model for the data, and even in those situations where we don't have a statistical model, a classical statistical model, but we can build it from the data. So without further ado, let's go on. The idea is seeing very rapidly the multiplicative model. Our first application in this field was in assessing the quality of Despeckling filters, and I think it's a good starting point for this presentation. Then we will move into models for intensity SAR data. You can imagine already that we will talk about the exponential, gamma, and so on very rapidly. Applications of these models when we join a model with information theory and with information geometry from a statistical viewpoint. Then we will see the most important model for polarimetric data, which is the Wishart distribution. And finally, I will mention briefly a new venue of research, which is about geodesic distances between Kenow projections of polarimetric data. So what is SAR? The image I always use to illustrate SAR is a bat. SAR is an active sensor that operates in the microwaves. And some of the basic characteristics that, of course, I don't have to stress here to this audience, but just to remind, is that SAR sensors are extremely important in remote sensing, both in applications and in the engineering and in the development of new sensors. Their application is very successful because data can be captured almost regardless of the weather conditions, because the sensor is active and it operates in the microwaves. These sensors measure essentially the geometry, and by geometry we refer to the texture, which is variations of the order of the wavelength, and wavelength, we are talking about centimeters to almost meters. And we also measure the dielectric constant of the target using SAR. And depending on the sensor and on the target characteristics, the signal is able to penetrate to some extent canopies and the soil, the surface of the soil. These sensors, as we have recently seen on LinkedIn, the beautiful images Capella is providing, these sensors can provide images with very high spatial resolution. All these beautiful properties come with a price. The price we have to pay is that we have to live with Speckle. Speckle is an interference pattern, which is better modeled, better described as a noise. So we will refer to it as Speckle noise. So just to compare, this is an old example that works quite well. This is an optical image in which we see many classes, and also we see clouds, and the same area as seen by a SAR sensor, theoretically, more or less the same time, we don't see the clouds. So SAR is little affected by clouds, but we don't see as many classes as we see in the optical image, except that we see very clearly the water. The water is very peculiar kind of target for SAR. But I am sure you all know much more about SAR and SAR applications than I do. So let's go into the multiplicative model, which is the basic assumption that we will make along this conversation. A well-accepted model for the return in each pixel for the measurement is the multiplicative model, in which Y describes the speckle and X is the backscatter. When we are talking about intensity SAR, the physics of the imaging allows us to say that Y, speckle, follows a gamma distribution with mean 1, and the shape parameter equal to the number of looks. Number of looks is a kind of processing. We can think of it like the local mean of independent observations. So in order to know the distribution of Z, the observed value, in order to know the distribution of Z, the observed value, since we already know the distribution of Y, gamma, and we may assume that X and Y are independent, we only need to stipulate the distribution of X, the backscatter. And what we want to retrieve from the data usually is the backscatter, because in the backscatter is embedded the information about the target. The only assumption we make so far about the backscatter is that it can be either a constant or a random variable with positive support. I will quote now one of my idols, George Box, statistician, in the re-edition of his book, 2005, he says clearly that the most that can be expected from any model is that it can supply a useful information, a useful approximation to reality, a useful approximation. In this sense, all models are wrong, because there is no model as precise as nature, as precise as what we already have our target in total detail. So I like very much the sentence, all models are wrong. Some models are useful. So we may be tempted to ask if the multiplicative model is correct, but that question is not fair because there are no correct models. The fair question should be, is this multiplicative model adequate? And I will show you an example. There are many examples in the literature. This is an SAR image over Oberpfaffenhofen in Germany. And this rectangle is from a bare soil or early crop area. And I took the samples from this area, from this region of interest. We have more than 15,000 pixels. Since it is a single look image and the area is homogeneous, we expect the data to follow an exponential distribution. And here are the fits, sorry, of the exponential models for the 3 intensity channels. This is a polarimetric image. So here we have the HH, HV, and VV channels. The fits are amazing. And that is one of the things that always fascinated me in SAR image analysis, that the physical models, they are so adequate. They are so good at describing the data that we have. And also, these statistical models provide us with a wealth of information, which is really, really valuable. So I could show you other examples, other samples, and we can usually fit the data quite well using distributions that arise from the multiplicative model. But we are not very happy, we're usually not very happy with Speckle. So one of the basic operations that we enjoy performing on SAR images is the Speckling. This area, this topic of filters for speckle reduction is very active, is still very active. There are fantastic papers in the IEEE Geoscience and Remote Sensing magazine, which provide a whole view of the area of speckle filters. But along with speckle filters, we have measures of quality. In the following, I won't go into details about the speckle filters, but I will be concerned about measuring how speckle filters perform. So what we'll be talking about? There are many despeckling filters, starting from, say, the mean, the median, Lie filter, enhanced Lie. It's a whole universe. And we are interested in measuring how well they perform. So our assumption is that is the multiplicative model in which the observation, Z, is the product of 2 independent random variables, X and Y. Y is the speckle, and it can be modeled as a gamma random variable. A speckle filter can be seen as an estimator X hat of the backscatter X. So we want to retrieve information about the backscatter using Z. How do we do this? By means of a filter X hat. The ideal estimator will behave in the following way. The ideal estimator would be, is X hat exactly equal to X. So my ideal filter will retrieve exactly the backscatter. So if I divide Z, the observation, by the estimation of X, and if X hat is perfect, I will be dividing Z by X, and Z is X times Y. So my ratio image will be Y, will be a collection of independent, identically distributed random gamma variables with mean 1 and shape parameter L, the number of loops. This simple result gives us a clue to measure the quality of a filter. A speckle filter will be good when it produces a filtered image that yields a ratio image that is very, very close, here comes an important word, close, to the hypothesis of the perfect filter. So my filter will be perfect if the ratio image is a collection of independent, identically distributed gamma random variables. So our idea is assessing the quality of a filter, of a speckle filter, by measuring the closeness of the ratio image to the hypothesis that this ratio image is adherent to the statistical properties of pure speckle. And notice that what I am using here is x hat, my filtered image, and z, my observed image. I don't need anything else but these two images. So we proposed measuring this closeness, or if you prefer, in fact, what we measure is the distance, by two components. The first component has to do with the first order statistics, mean value and preservation of the equivalent number of loops. And the second order component is second order statistics that measures the remaining geometrical structure. The ratio image should not have any geometrical structure because it should be comprised of independent, identically distributed gamma random variables. So where does this idea lead us? We have here an example of a simulated SAR image in which we have a dark background, a bright foreground, and small, very bright points. With this, we are simulating corner reflectors. This is the noisy image, and this is the result of applying 4 state-of-the-art filters: the improved Lie, FANS, SRAD, and PPB. They are different in their conception. Some of them use the idea of a diffusion process, others are Bayesian, others are merely statistical. They're essentially different, and they produce different results. What is evident, what strikes our sight, is that Lie and SRAD do not preserve well the edges. You see, the edges are blurred, whereas FANS and PPB preserve the edges quite well. And if we concentrate on FANS and PPB results, the main difference between them is that PPB kills or reduces a lot this bright point and this bright point. So those should count against the quality of PPB, more or less in the same sense that the lack of preservation of the edges should count against Lie, improved Lie, and SRAD. Let's look at the ratio images. Remember, a ratio image consists in taking the noisy image and dividing it point by point, pixel by pixel, by the filtered image. What do we obtain? These are the 4 ratio images. Notice that the lack of edge preservation of the improved Lie filter appears as a remaining geometrical information here. SRAD also shows this remaining geometrical information, but I don't know if you can see it on your screen. Also, it shows me that it has blurred the small points, the corner reflectors. Whereas I don't see any geometrical information in FANS or in PPB. So most likely I will choose between FANS and PPB. Now let's apply this idea of measuring the distance between these images to the model. So we will measure the distance between data and a model. What's the data? The ratio image. What's the model? The idea of having a collection of independent, identically distributed gamma random variables with mean 1 and shape parameter L. Let's measure those distances. Well, these are the distances. The closer, the better. So our worst filter is PPB, surprisingly, because we don't see any geometrical structure here, but PPB, remember, has killed 2 right points, and that counts negatively. That puts PPB far from the ideal situation. PPB is followed by ELE, which is followed by SRAD, and the best result is FANS. So we followed this idea, we implemented a system, and we made a couple of publications about this, relatively recent publications, where we provide the code and the data so you can use this measure. We called it M measure, M for measure, of the quality of a filter. So the idea behind the technique is that we measure the distance between 2 objects, 2 very different objects, a theoretical distribution and observed data. And this has inspired many other works in the field. The idea of comparing samples or samples and models, this idea, this very simple idea, has led us to interesting and funny to obtain interesting studies that have produced interesting tools. So in order to proceed, I will need to invest some time in the multiplicative model. We will keep the hypothesis that the speckle noise is gamma, but now we will assume a distribution, a particular distribution for the backscatter. We will assume that the backscatter follows a reciprocal gamma distribution. Why this? Because it leads to the G0 distribution, which is characterized by this density. I don't know if you have worked with it, but most likely you have seen in the literature the K distribution. The K distribution assumes that X follows a gamma distribution, and the density of the K distribution includes a Bessel function, and everything becomes complicated when the Bessel function appears. Whereas the G0 distribution does not include the Bessel function. In fact, this distribution is a scaled version of the Fisher-Snedeker or F distribution that we are all quite aware appears in statistical tests. The interesting thing, among other nice features, is that alpha, that in this parameterization is negative, measures the textural contents. And gamma is scale parameter. L is the number of loops. So we will assume this distribution for intensity data and we'll derive techniques. Well, I mentioned some of the advantages and disadvantages of the G0 distribution. Among the disadvantages is that the likelihood function that we use to estimate parameters, it may become flat in some areas. And when it becomes flat, it's very hard, not to say impossible, to maximize and thus to obtain estimates. The moment estimators may not have solutions. And these estimators, both maximum likelihood and moments, are susceptible to outliers. So we came to this idea. Since we are already playing with distances between data and models, how about proposing as an estimator the point in the parameter space which minimizes the distance between the model, so this is the part that will vary, the model, the G0 distribution, the G0 density in particular, we will minimize the distance between the model and what is fixed. What is fixed is smoothed version of the histogram. So the data enters here, Z, we form the histogram, we smooth the histogram with a kernel to make it smooth. And then we seek for the parameter theta that minimizes the distance between this smoothed histogram and the density. And this will be our parameter. Which density? There are infinitely many densities between these things. Well, we chose to work with the triangular or symmetric chi-square distance, and it works quite well. How does it work? Well, we have a histogram, then we form smoothed version of the histogram, and then iteratively we seek for the parameter theta, which is alpha and alpha and gamma, which minimizes the distance between the smoothed histogram and the density. And in this case, we come up with this red density. Advantages of this technique. It is really, really less sensitive to outliers than classical techniques. Of course, because we are not using the data directly. The data enters in the formation of the histogram. And it also performs quite well with small samples, with large samples. So it's a very good estimator, sorry. What's the price we have to pay? It is computationally much more expensive than moments and than maximum likelihood. But it's advisable to consider using it in practical situations because of its good properties. Why did we choose such a distance? Why did we pick the chi-square, symmetric chi-square distance or triangular distance? Well, the symmetric chi-square distance is a member of a family of distances that can be formed by choosing two functions, the function h and the function phi. With these two functions, we define a divergence between two distributions. What is an h-phi divergence between two instances of a model, between two densities of the same distribution with possibly different parameters, theta 1, theta 2. First, we compute the ratio of the densities. Once we have the ratio of the densities, we transform this ratio by the function phi. Phi is convex. And then once we have to obtain this, we integrate with respect to the second model. So this integral is the expected value of phi, the ratio, with respect to the distribution given by the second model. And once we obtain this expected value, we transform it by a strictly increasing function h. The only conditions that we impose on h and phi are that h is strictly increasing and starts in 0, and phi is convex, and very mild smoothness properties. First derivative for h and first and second derivative for phi. Almost nothing. Very, very mild conditions. This defines an h-phi divergence. But we were talking about an h-phi distance. These divergences may not be symmetric. So we introduce symmetry by taking the average of the dh phi from model 1 to model 2 and the dh phi divergence from model 2 to model 1. This expression here, trivial, very simple technique. So what do we gain here? Well, first of all, the chi-squared distance belongs to this family. Good. But also the Bhattacharya, the Kurbach-Leibler, the Remy of order beta, the triangular, the harmonic, the Hellinger, my favorite, the Habda-Sharvat, Sharma-Mittal, many, many well-known distances, divergences, are obtained by choosing adequately h and phi. So we have a beautiful theoretical context, but we have more, we have much more than this. But before I tell you the rest of the story, let me introduce another family of distances, of divergences. I will use the term distance and divergence in the same sense, but always think of distances. We have a beautiful way of measuring the distance between distributions due to Rao. It was proposed in the 50s, last century. It's obtained by studying small perturbations of a distribution and measuring the distance between the original model and the perturbed model. The mathematical aspect is a little bit complicated. It requires differential geometry, requires computing geodesics on probability space, on the probability spaces, but the essential part is the following. We may obtain a geodesic distance between two models, two members of the same model, but indexed with different parameters, θ1 and θ2, by considering the square root of a quadratic form. This quadratic form, imagine, could be something like the Euclidean distance, but it's not the Euclidean distance. It is a distance that depends on the information matrix of the model. So these distances, these geodesic distances, incorporate the geometry of the model. They are often tough to compute, but they also have beautiful properties. One of the most beautiful properties is that this expression 2 can be connected to generalized entropies in the same way that we have H-phi divergences, we have H-phi entropies, and we can express 2 with H-phi. With H and phi, the same conditions of H and phi with the divergences. So everything matches in a beautiful mathematical framework. So what do we have so far? We are able, at least from a theoretical viewpoint, to measure the distances between models. And we can say that we can compare 3 models. We can compare model 1 with model 2, model 1 with model 3. But do we have a notion of close and far? Can we say that model 1 and model 2 are very close, so close that they can be considered the same model? No, we don't have that information. We have numbers, but we don't have a semantic. We don't have semantics for those numbers. Can we compare those distances? Can I say anything about the Kullback-Leibler distance when I know something about the Hellinger distance? No, they are not comparable. The Kullback-Leibler is between 0 and infinite. Hellinger is between 0 and 1. So it's a beautiful mathematical construct, but not very useful so far. But now becomes the useful part. When we index any of those distances by the maximum likelihood estimators of θ1 and θ2, notice here that this is a distance, h5, indexed now by the maximum likelihood estimators, θ1 and θ2 hat, and these estimators have been computed with samples of sizes n1 and n2, and of course, asymptotic theory, n1 and n2 large, etc., etc. This quantity, and look, this quantity is very simple to compute. Once we have the h5 distance, we only need the derivative of h at 0 and the second derivative of phi at 1. The rest is a function of the sample sizes. Well, under the null hypothesis that the parameters are equal, this quantity follows asymptotically a chi-square distribution with p degrees of freedom. Chi-square with p degrees of freedom. whichever h and phi. So the Hellinger distance, the Kullback-Leibler, the triangular, whichever you imagine, is transformed into a test statistic with the same asymptotic distribution. So they are comparable. That is very nice. We have semantics, and these quantities are now comparable. We can state more or less the same result when we handle differences of entropies, generalized entropies, H-phi entropies, indexed by maximum likelihood estimators. The details are on the papers. I don't want to go into details right now. I want to go as soon as possible into the application. So what can we do with this? Well, we have test statistics based on information theory. We can use the H-phi divergence to be turned into a test statistic, and each H-phi entropy to be turned into another test statistics. And we have test statistics based on information geometry, because we can connect the entropies with the geodesic distances and everything goes smoothly. Well, all the results are based on asymptotic theory, so very large samples. But we have made studies with small samples, and they behave quite well. They are very, very well approximated by the theoretical distribution. So even if I have, say, examples of size 4, the test statistic based on entropies is very good. It already follows approximately, very close, a chi-square distribution. So everything is interpretable, everything is comparable, and we have very good tools, very interesting tools. Example, where can we use this? Imagine we take a very fine strip of data from a SAR image, and this strip of data contains an edge. Here I am illustrating with a strip of width, I don't remember exactly, but maybe 10 or 20. But in our applications, our strip is of size 1 pixel, and you will see an application later on. So our problem is finding where the edge is. Okay, so we apply what we know as the Gambini algorithm that consists of the following. Take a sample at the beginning of the strip, estimate its statistical properties. Use the rest of the observations as the other sample, estimate the statistical properties, and compare them. Repeat this idea by advancing like a cursor and taking progressively a larger sample to the left and a smaller sample to the right. At each step, you estimate the statistical properties of one side and compare them with the statistical properties of the other side. By statistical properties, of course, you may imagine the mean. The mean standardized, like an F-test, but we can also imagine a stochastic distance, a test based on stochastic distances, or a test based on the difference of entropy, or a test based on the geodesic distance between models, between G0 models. What do we obtain? Well, we obtain this beautiful result. For instance, for the single loop case, which is very noisy, the noisiest case, you can see the orange curve is the geodesic, the test based on the geodesic distance. And this is the point at which the statistics is maximized. So this is where the sample to the left is most different from the sample to the right. And it allows us to detect the point where the edge is. But by the same price, since we are handling statistical tests with non-asymptotic distribution, when there is no difference, our test will not find anything. So we will have this red line here below that says, well, there is no edge there. And that is also valuable information. We made a very simple application. We took this image and an area around this region, around this corner. And here is the result of applying the Gambini algorithm over the test statistic based on the geodesic distances per line, one test for each line. So a strip of height one pixel. And you see that we find the edge quite well. This was repeated in the Monte Carlo study, etc., etc. It performs quite well when compared also with state-of-the-art edge detectors. And it has the advantage that it doesn't produce too many points because we obtain 1 point per line or 0 point, 0 or 1 point. In this case, every line has produced a point. Nice. So we saw two applications to intensity data, three applications to intensity data, performance of Speckle filters, parameter estimation, and edge detection. What can we do with polarimetric data? It becomes, in principle, much more complicated because the data now are matrices, complex matrices. At each pixel, we have a complex matrix, but we have a model. We have, in fact, several models, but we have a very successful model for this polarimetric data, which is the Wishart distribution. The complete name is the complex Wishart distribution, the scaled complex Wishart distribution. It is characterized by this density. It is a generalization of the gamma distribution. At the end of the slides are many references, if you want to go into the details. And we were lucky enough to be able to compute stochastic distances between these Wishart models. And the expressions are relatively simple. They're surprisingly simple. They rely only on the number of loops and on the determinant and the inverse of the covariance matrix. And they have very good performance, even for samples of size 4. If I want to compare two samples of size 4, these test statistics based on divergences perform very, very well. So we applied the same idea, the Gambini algorithm, but now to polarimetric data using stochastic distances. And here we have the results with the Kullback-Leibler, Renyi with one parameter, Renyi with a different parameter, Hellinger, Bhattacharya, and also the maximum likelihood technique, and we obtain very good results. The image looks simple, but here we exaggerated the contrast. This is the famous San Francisco image. You live in, well, half of the audience probably lives there in San Francisco. Probably you are tired of seeing this image, but it is very, very interesting. And the problem here was trying to find an edge between C and other classes, and these techniques perform quite well. I will go very fast on this application. You have one of the co-authors of this paper, Shonak, here. The problem with polarimetric images is that depending on the orientation of the target, in particular in urban areas, when the urban area is aligned with the line of sight of the sensor thinks that that is a volume. It has more volume scattering than it should be. Volume scattering comes from, for instance, forests. So we took an area, this sample A of San Francisco. We know in this area there shouldn't be too much volume scattering, and we applied a classical technique, the Yamaguchi 4 components rotation, to alleviate this effect. And this classical technique reduces the volume component of the scattering from 95% to 93%. Well, okay, it reduced this volume scattering, and this reduction goes into the double bounce, which is the correct backscattering. We proposed another technique which consists in rotating in such a way that we maximize the distance between the rotated data and the original data with restrictions, but it is relatively simple. It is a relatively simple technique, and we obtain from 95 to 74%. So a significant reduction of the volume scattering, and most of this reduction goes into double bounce as expected. This technique, well, it got the attention of the people from ESA, and it was implemented, it was incorporated into the latest version of Pulsar Pro. Well, I am very proud of reading here that developers of Pulsar Pro called it the Bhattacharya and Frery decomposition, and it performs quite well. And it's fast, very, very fast. That is a feature of all these distance-based techniques. You probably will have to spend some time with pen and paper, but once you have the theoretical results, everything is very fast. So what else can we do? Non-local means, we can perform non-local means for speckle reduction in polarimetric images. How do we do non-local means from a statistical viewpoint? We want to compute a convolution mask that changes from position to position. It changes at every pixel. And the convolution mask is composed of weights. So what is the weight of this point, W1? The weight W1 results from comparing all the observations around the corresponding pixel, which is this one, with all the observations surrounding the central pixel. So the observations in orange will be compared with the observations in red. Notice, the samples don't have to be the same size. They can be different size samples. So what do we do with these orange observations? With these orange observations, we compute the one estimate. With the red observations, we compute the other estimate. And then we compare the estimates with stochastic distance. This stochastic distance becomes a p-value, and the p-value becomes a weight. And we do this, sorry, I changed, the colors are wrong. This should be orange and this should be green, but this is the idea. We perform these comparisons at each position within a search window using estimation windows that don't have to be of the same size. So you can imagine we can put an adaptive technique for estimation. We can embed it into the non-local means. Does it work? It works beautifully. Again, San Francisco, the box car filter, which is the mean, the local mean, of course, it reduces speckle, but it kills the information also. And this is the result of applying the non-local means filter based on the Hellinger distance. The result is very good. It's very good at preserving details, and it reduces speckle. And you can see it on the paper. It also preserves the signature, the polarimetric signature. So performs quite well. Which other application can we use? Well, we can classify segments. This is a polarimetric image from Brazil. This is a river, the San Francisco River. These are agricultural parcels. We first segment this image with a very simple classifier that was proposed for optical data. So very simple. And we over segment the image, we obtain this. Then we find samples, training samples over the polarimetric image, and we build models. And finally, we classify the segments to the model which is closest. In which sense? In stochastic distance sense. And the results are also very good. Finally, difference of entropies. So far, we have seen techniques that allow us to compare two objects, two samples, two models, data, and a model. But what happens when we want to compare more objects, for instance, in a time series? Well, we have to rely to the more general approach, which is with the difference, the squared difference of entropies. And the techniques work quite well. Remember that we have generalized entropies, the Shannon entropy, the Renier entropy, the Salis entropy, Harda-Sharvat entropy. We have many, infinitely many entropies. We have this example of a polarimetric image over suburbs of Los Angeles. Date 1, date 2, you see that the urban area has expanded. This map, this binary map, was made by visual inspection by an expert, and this is the map we obtained by computing the square of the differences of entropies using windows of size 4 pixels, 2 times 2, and we compute the difference, and we decide if the difference is statistically significant or not. Since we can use p-values, we don't need to make a binary mask. We obtain a result that measures the evidence of change. And the results are, again, very good. Finishing, just a very fast idea of what we are doing now. Pulsar data consists of, at each pixel, a matrix of complex values. This matrix can be projected in a smaller dimensional space. One of these projections, very interesting projection, is called the Kenau projection, that transforms this complex matrix into a real valued vector that lies on the surface of a 16-dimensional sphere. If we want to measure distances on the surface of this sphere, so data which was projected with the Kenau projection, what's the distance between points on the surface of a sphere? It's an angle. So everything becomes very simple because now we measure angles, and with these measures we may decompose the observations in elementary backscatterers, and well, all we do with polarimetric data can be done on the surface, on the Kenau surface, the surface of this 16-dimensional sphere. And one of the things we are studying now is the statistical properties of these projections, which is an open problem. My concluding remarks. Thank you for surviving up to this point. We have posed several interesting problems as measuring distances between objects. And using information theory, statistical information theory, and statistical information geometry, we can provide such measures with semantics because they are test statistics with known asymptotic distribution, which are computationally feasible. They are very easy to compute, and they provide us with very good solutions. As I said at the very beginning, although everything I presented was for SAR and pulsar, these techniques perform quite well in other areas. They have been also used in tomography, where the authors use these techniques for Poisson observations. Sorry, they have also been used in echography, where the model is Rayleigh. other models specific for echography. And when we don't have a model, we can also do this. And this is an invitation if you want to perform research on this area, leading to a beautiful PhD, if you don't already have one. This is a very beautiful topic. This is a very nice research area. Some of the questions, well, everything I stated depends on maximum likelihood and large samples. What happens? What happens in particular when we use kernel estimators? Can we obtain other geodesic distances? We have only worked with the Shannon. Can we devise other useful techniques? And what can we say about the statistics of the Kenau projections? So this is my contact, and thank you very much. Very glad to talk to you. Here I will stay for questions, suggestions, threats to my life, whatever. Okay, Shonak, I think it's with you now.
Thanks for the talk, Alejandro. This is Neil. One of the questions I have from long exposure to this stuff, going all the way back to the Venus Magellan probe, was, does having better knowledge of your pattern, and maybe Valerie can speak to that too, improve this processing you're trying to do?
Sorry, the sound was cutting. Could you mind repeating the question, please?
I thought I unmuted. Can you hear me?
Yes, yes, I can hear you now.
Okay. The question I asked was, where in this processing would adding additional information on the pattern of your radar play into things?
The radar pattern, do you mean the signature? I mean the radar signature?
Well, it has side lobes and beam widths and so forth.
Ah, beautiful question. How do we relate this to the physics of the antenna? I have no idea. That is totally open, totally open. Yeah, very nice.
Oh, another research topic. Okay.
Yeah, sure. There are so many. And just one clarification. It may seem that we are assuming fully developed speckle. That's not the case. When we introduce other distributions other than the gamma, we are allowing for the possibility of not fully developed speckle. So there is a connection that can be exploited.
Yeah, I remember reading through the original theory, there was a place for it, but most of the time it seemed like we're just going to call it 0 and 1. And I guess your boxcar filter, as you were calling it, was kind of that.
Well, a boxcar filter is a convolutional filter in which all the weights are equal and they don't change when the filter moves. So this non-local means is a generalization. The boxcar is for sure is a particular case of the non-local means, but a very bad one.
So it does look like we're at time, but I'm willing to stay a couple minutes later if anybody has some additional questions for Dr. Frery. And thank you very much for the presentation. Really illuminating.
Totally my pleasure. Thank you very much for the invitation. You have my contact, and if you want to send questions, suggestions, I am very happy to see them. Okay.
One thing I wanted to mention too is that we could, with your permission, we could post this to the GRSS YouTube channel. We would get some great traffic. That would be excellent.
Thank you very much. I'd love that. Okay, so welcome. Thanks to everyone, and bye-bye. See you in the next initiative.
Thank you.
Thank you very much.
Bye.